Hello, and welcome to the next exciting installment of Digital Design. The topic of this video is number systems, in particular signed numbers. So there are two common ways that binary numbers with negative values can be represented. One is called signed magnitude, and the other is called 2's complement. In signed magnitude numbers, the most significant bit is called the signed bit, and the remainder are the magnitude bits. So the signed bit determines whether the number is positive or negative. A 0 means positive, a 1 means negative, and the other bits are summed up as usual. So if I wanted the number 6 represented as a 6-bit signed magnitude number, number 6 is 110 with the 3 bits of magnitude, and then the sign is 0 for positive. Number -6, the magnitude again is 110, which makes 6, and the sign is 1, meaning negative. So an n-bit signed magnitude number has a range from negative 2 to the n minus 1 minus 1 to 2 to the n minus 1 minus 1. For instance, a 3-bit signed magnitude number has a range of -7 to 7 for a 4-bit signed magnitude number. Another strange thing about signed magnitude numbers is there are two zeros. There's a positive 0 and a negative 0. Let's make that look more like a 0. Plus and minus 0, which represent the same value of 0, which is a little weird. And another problem with signed magnitude numbers is addition doesn't work properly with simple binary addition. So signed magnitude numbers are not the most popular system. 2's complement numbers have fixed these problems. Addition works, and there's a single representation for 0. The way a 2's complement number works is the most significant bit has a weight of negative 2 to the n minus 1. So for example, a 4-bit 2's complement number, the columns have weights of 1, 2, 4, and instead of 8, negative 8. So the most positive 4-bit 2's complement number would be no negative 8s, a 4, a 2, and a 1, which makes 7. The most negative would be a negative 8, no 4s, no 2s, no 1s, and that's negative 8. The most significant bit still indicates the sign. A 1 in the most significant bit means negative, and a 0 means positive. And the range goes from -2 to the n minus 1 to 2 to the n minus 1 minus 1. So in the case of 4-bit numbers, this goes from -8 to +7. That's a little interesting that the range is asymmetric, but there's no negative 0 now. There's a method to flip the sign of a 2's complement number. It's known as taking the 2's complement, and what you do is invert the bits and add 1. So let's say we had the number 3, which is 0, 0, 1, 1, and we wanted to get -3. We wanted to negate it. We'd first flip the bits, 1, 1, 0, 0, switch zeros from 1s, and then we would add 1, and we'd get 1, 1, 0, 1. This is a 1 in the negative 8s column, plus a 1 in the 4s column, no 2s, plus a 1 in the 1s column, which sure enough is -3. Let's do another example. Let's find -6 by taking the 2's complement of 6. First we flip the bits, 1, 0, 0, 1, and then we add 1, 1, 0, 1, 0. Similarly, let's say we had the 2's complement number 1001, and we want to know the decimal value. Two ways we could get at it. We see this as negative. We could go directly. It's a -8, no 4s, no 2s, plus 1. So this is -7. Or since it's negative, we could take the 2's complement to make it positive. So taking the 2's complement of this is 0, 1, 1, 0. Flip the bits, plus 1, 0, 1, 1, 1, which is positive 7, so we know the original was negative 7. Addition works in 2's complement. For example, let's do 6 plus negative 6. 0 plus 0 is 0. 1 plus 1 is 0, carry a 1. 1 plus 1 plus 0 is 0, carry a 1. 1 plus 0 plus 1 is 0, carry a 1. We get an overflow out that we discard, and we're left with 0. Similarly, let's do negative 2 plus 3. Negative 2, well 2 is 0, 0, 0, 1, 0. So let's invert the bits. Plus 1 makes 1, 1, 1, 0. So this is negative 2. This is positive 3. 0 plus 1 makes 1. 1 plus 1 makes 0, carry a 1. 1 plus 1 plus 0 makes 0, carry a 1. 1 plus 1 plus 0 makes 0, carry a 1. And again, drop that overflow, and we're left with 1. So negative 2 plus 3 equals positive 1, as we'd expect. We can perform subtraction by flipping the sign and then adding. So let's say we wanted to do 3 minus 5. That's the same as 3 plus negative 5. 3 is 0, 0, 1, 1. Negative 5 is 1, 0, 1, 1, which we could have gotten by a 2's complement. And we add them up, and we get 1, 1, 1, 0, which is negative 2. So sure enough, subtraction works. So let's summarize by comparing the range of numbers. Unsigned numbers, say for a 4-bit number, would go from 0 to 15. A 4-bit 2's complement number would go from minus 8 to positive 7. And a 4-bit signed magnitude number would go from negative 7 to positive 7 with both positive and negative 0.